Okay, great. Thank you so much for having me. Yes, my name is Emily Liepold. I'm a postdoc at UC Berkeley, and I'm going to talk to you guys again about some of the work that I've done in collaboration with other members of our group, especially Matthew Quenneville, Jacob Plow, and Shanghai Ma, to use KCWI to reveal the intrinsic shapes and central black hole masses of the most massive galaxies in our neighborhood. So I'm going to just sort of assert that big galaxies are really interesting objects. So by big galaxies, I mean stellar masses above like 5 × 10⁻¹1 solar masses. These are fairly rare objects. On the right side, we have a galaxy stellar mass function from a paper we put out last month. There are only like a couple hundred of these within, say, 100 megaparsecs of us. These are also often the endpoints of mergers and evolution. So if you want to understand those processes, these are good things to look at. They're often sometimes, but not always, the brightest galaxies in their groups or their clusters. So they're also important for understanding those larger structures as well. And the sort of center of a lot of the stuff that I focus on is that they often host ultramassive black holes above about 1 billion solar masses. So how would we go about finding a supermassive black hole in one of these galaxies? So the technique I use is called integrated stellar dynamics. And the notion here is relatively straightforward and intuitive. So if you have a relative velocity between you and a single star, you'd expect there to be a Doppler shift in that star spectrum. If you then have a population of stars that all have different relative velocities, you then expect a distribution of Doppler shifts. And if you can measure this very precisely, you can work backwards and do lots and lots of modeling and figure out what the mass distribution of the galaxy looks like. So to do this, you need a number of things. First, you need a bunch of spectra, because that's where you'll actually see these Doppler shifts. You need those spectra to have extremely high signal noise, because the features you're going to be looking at are absorption lines that are fairly faint within the realm of the spectrum. And you want to measure the entire velocity distribution, not just the mean and the width, but the entire thing out to, like, say, the first 8 moments of that distribution. You also need high spatial resolution so that you can probe all the way down to the region that is dominated by the black hole, all the way out to the region that's dominated by dark matter. And then finally, you need to do lots and lots of modeling. We use a technique called triaxial Schwarzschild modeling, which I'm not going to talk about today, but you can basically write a whole PhD thesis about that. But instead, I'll focus on the first 4 things, which are satisfied by KCWI. So an example of this, we looked at the massive galaxy M87 using KCWI. So this is, of course, probably the most famous massive elliptical galaxy. It's been studied for like half a century. It was the target of the Event Horizon Telescope. And in some existing data, there are sort of indications that the intrinsic shape of the galaxy wasn't what was previously assumed in previous work. So we said we want to get some Keck data for this to really figure out what's happening in M87. So we looked at it from 2020 to 2022. We used it in sort of this mosaic sense, where we built up this enormous picture of the galaxy that's roughly 23 kiloparsecs by 28 kiloparsecs, or about 100 arc seconds, 150 arc seconds in both directions. In total, about 13 hours on target, 3 hours on sky. And with this, we build out this extremely exquisite picture of the galaxy. I also want to point out that most of those pointings are actually below the sky level, which makes it, of course, extremely tricky. You have to be really careful about your sky subtraction. So KCWI allows us to get extremely high signal noise spectra. Here we have a bunch of bin spectra. We have about 500 of these in total for this galaxy. And I want to point out that the innermost ones have a signal noise of like 200 per angstrom. And the outer ones into this area that's extremely sky dominated are still like 100 per angstrom. This allows us to fit the entire velocity distribution of the galaxy. This is the first 2 moments. So we see that there's a strong rotation in the velocity distribution. We see that that's misaligned with the photometric major axis. And we see that the velocity dispersion rises really quickly towards the center. So this is an indication that there's probably a black hole there, but we've known about that for like half a century. So what we did is we performed the first simultaneous measurements of the 3-dimensional triaxial intrinsic shape of M87 with its central black hole mass, and found that there's a black hole that's, I don't know, something like 5.4 billion solar masses. And the average axis ratios, the stellar halo, are like 1 to 0.85 to 0.72. So it's a bit squashed in both of the principal directions. This is also kind of exciting because Hubble tweeted about it, referring to it as a space potato. And I think that's like the closest thing to a claim to fame that I have. Okay, so we learned a couple things along the way. One thing was that the line spread function of the large slicer configuration of KCWI is slit limited. So instead of being sort of a Gaussian thing like we have for the small slicer, it's instead sort of flattened on the top. And you can treat it as a convolution of the top hat and a Gaussian. This turns out to be really important because what we actually observe in these absorption lines is the convolution of what's happening in the instrument and what's happening in the galaxy. So really characterizing this well is important for getting robust results. We also did some fun PCA decomposition to handle some of the sky subtraction. We found that some of these extremely sky-dominated exposures still wind up with sky features in the end, because it's really hard to get it perfectly subtracted when you're 2 magnitudes below the sky. So we fed all of the sky spectra that we have into a PCA decomposition, took the most significant features, and fed that into our spectral fitting as additional additive components. And we tend to get very robust results when we do this. And then the last thing that I won't really mention more of is that we we built some routines to basically feed KCWI data cubes into the Gemini, GemCubes, and NIFCubes routines to allow for mosaicing and drizzling of this data, which was a lot of fun and allowed us to implement these without needing to actually reinvent the wheel at all. Okay, so the remainder of this talk, I'm going to talk about some ongoing work that's hopefully out in the imminent future on the galaxy Holmberg 15A. So Holmberg 15A is the brightest cluster galaxy of Abell 85. This is a fairly distant galaxy. It's about 250 megaparsecs away from us. And it's a fairly famous galaxy for a couple of reasons. One is that it has the largest known core of any early type galaxy that we're aware of. The core is about 3 kiloparsecs wide. It also, for cored early type galaxies, has the faintest central surface brightness. We can see on the right side the surface brightness profile compared to M87, which is marked in red. But we see that it's extremely faint and has a similar shape, even though it's 15 times further away. So this really tells us that this galaxy is enormous. Both the size of the core and the central surface brightness are correlated with the black hole mass. So these are two features that suggest that the central black hole is going to be one of the largest we can find. Okay, so what did we do? So we looked at this again with KCWI, again in this sort of mosaic sense, building out this sort of mosaic that extends well outside the region where this is sky dominated. This entire field of view spans about 100 kiloparsecs by 100 kiloparsecs in this galaxy. So recall for M87, it was like 25 by 25 kiloparsecs. This is 4 times further out in the physical scale. This is also extremely sky dominated. You can see that the region where you actually have majority galaxy photons is really just the central pointing. So this is something that it was extremely difficult to reduce. But even once we do that, we get very high signal to noise spectra, especially once we sort of handle some of the additional sky diffraction I was talking about. In the centralmost regions with the small slicer, we get signal noise of something like 130 per spectral pixel, which is happening for the small slicer. And even at the outermost bins, 2 magnitudes below the sky, we still get signal to noise of about 60. So this is a really incredible feature that's not really possible with any other instruments. It's incredible sensitivity. Okay, so sort of the last piece here, I want to point out that with KCWI, even in these extremely faint regions, we're able to get very good measurements of the velocity distributions all the way out through the first 8 moments of the distributions. In the top panels here, we have the first 4 moments from the small slicer data looking right at the center. We see that there's a small sense of rotation here. We see that there's the same central uptick that's associated with the central supermassive black hole. And we have features in the higher moments as well. Even into these outermost regions that are 100 kiloparsecs from the center, we see evidence of large scale rotation. and sort of an uptick in the velocity dispersion that's associated with perhaps starting to probe the cluster mass instead. So we then fed all of this into our triaxial short shield modeling, ran hundreds of thousands of hours of simulations, and a little bit of a spoiler for the paper. We find that it, along with NGC 4889, have the largest supermassive black holes that we know about from dynamical methods. This one is about 22 billion times the mass of the sun. We also found that the stellar halo of the galaxy is triaxial. So this is something that is only enabled with sort of the new modeling tools that we've developed, and the data is only enabled with the extreme sensitivity of KCWI. So I think I'm going to kind of leave things here. I do also want to plug that H15 is sort of the first out of our sample that we've actually been able to model. We have 3 additional galaxies that we model, or that we have already observed with KCWI. And now that we have H15 working and cooperating, we're excited to move on to those as well. So thank you so much.